Thank you for having me. So I'm Xavier. I'm a PhD student here in Paris at the LMF, um, where I'm studying the verification of Rust programs. And today I'd like to talk a little bit about the prototype tool we've been building called Creusot, which is meant for the verification of Rust programs and built on top of the Y3 verification platform, also developed at the LMF. You can find Creusot currently on my GitHub. You can compile it locally and try playing around with some programs. It can actually verify things, but the user experience is nowhere near as polished as, for example, that of Krusty's, at least for the moment. We'll see about the future. But the overarching goal with the work on Creusot is to help make the verification of pointer programs more practical, at least more practical than it would be in languages like C, where we just have sort of raw pointers. And to do this, we want to leverage the guarantees of the Rust type system to help simplify verification. So in particular, the thing that is of immediate interest is, of course, the verification of programs that use borrows in Rust, because unlike in C, where all we have are raw pointers, and thus we find ourselves required to use things like memory models and separation logic to help reason and break down the problem of verifying pointer programs. In Rust, we can leverage the discipline of ownership and the lifetimes of our borrows to help dramatically simplify their verification. So Creusot is a tool that for the moment only handles safe Rust, and in particular works from Mir, and translate those Rust programs into a functional language. And what we end up doing is that we encode our mutable pointers, our mutable borrows rather, using an approach developed by Rusthorn, where we use non-determinism to sort of sidestep the problem of mutation. So for those who may not be familiar with Rusthorn, the idea of this translation is that we're going to represent a mutable borrow as a pair of the values being pointed. So we have the current value and the final value of our borrow, which we prophesize at the moment we create a borrow. The intuition from this kind of comes from this diagram below, or at least hopefully does. The idea being, if we have some variable A, originally we have all the permissions on A. We hold the ownership of A, but the moment we create a borrow B of A for some lifetime alpha, we lend those permissions. And so for the duration of alpha, we can no longer refer to A anywhere in our program, but instead we have to modify it through B. And at the end of alpha, we recover those rights to use A, our variable A, and read and write from it. At that exact instant where we recover those permissions, the value that's now in A must necessarily be the last value that was being pointed to by B. And so that's exactly the intuition behind our translation, where the moment we create our borrow B from A, we're going to make a non-deterministic choice and guess the final value of our borrow. We're going to immediately give it back to A, the variable we just borrowed. So we're just updating A in advance of any changes we'll make to B. And so then all we have to do is continuously work with B, do all of our mutations. So for example, assign 5 inside of B. And then at the moment that B falls out of scope, at the moment that in Rust, this would be a drop, we place an assumption. And this assumption refines our knowledge of the final value of B and effectively tells us, well, B is just about to die, so whatever the current value of B is at that moment must be its final value. And thanks to this assumption, we're able to easily conclude, for example, here, that A must be 5. So we were able to show the correctness of this translation on paper through a fairly tedious syntactic proof. And so it's a little bit unsatisfactory. And as a result, we've been collaborating with the author of Rusthorn, one of the authors of Rusthorn, Yusuke Matsushita, on a new mechanized proof based on a semantic foundation and implemented as an extension of Rustbelt, the correct formalization of the Rust type system that we heard about on Friday. And this translation that I've briefly discussed so far is sufficient to show the safety of a Rust program. That is, its panic freedom, or rather its memory safety. And if we want to go further and start talking about functional correctness, then of course we need to start talking about our specifications. And that's one of the questions that we've been looking at recently, and we've been developing a specification language based in the tradition of ACSL, the specification language for the FRAMA-C verification toolkit for C programs, and Gospel, the generic specification language, which is for OCaml programs, and is used by the tool Camelier, for example. And in the context of Rust, one of the most interesting questions that we can ask ourselves for our specifications is how we're going to express properties on borrows. And so as we just heard previously in Prusty, there's this notion of pledges, which allows us to essentially specify properties that are going to hold at the end of a borrower's lifetime. And so we can sort of talk about the future through pledges. And we've actually chosen to go with a slightly different approach, which we can experimentally call prophetic values, where we allow specifications to directly refer to the final values, to the future values of our borrows in specifications. And this approach has also been used in Ada Spark to write specifications on the new form of borrows that they added recently to their language. So more concretely, in our program logic, so we have our logical terms, which are a fragment of pure Rust expressions. So in particular, all your sort of data type constructions for sums and products, constants, matching, as well as function calls and various basic operators and comparisons. But then on top of that, in particular, we add two sort of new operators, which are this t at fin and this t at now, which we use to refer to mutable borrows in specifications. And we also equip, since we want to write specifications, we also equip ourselves with a set of logical predicates, or rather propositions. So we have, for example, universal and existential quantification. So what are these two operators, t at fin and t at now? As I said a little bit earlier, we allow specifications to refer directly to the final values of our borrows. And so this t at fin denotes the value of a borrow at the moment it's going to be dropped, whereas t at now rather intuitively denotes the value of a borrow in the current memory at the moment that we're writing our specification. And so how do we use these to actually write a sort of useful specification? If we look at this simple increment function here on this slide, we'd like to say something along the lines of, after we execute the increment, the value that was inside of A will have been added, will have had the value of B added to it. And so that's exactly what we end up saying with our specification, where we say the final value that's going to be stored in A will be the same as its current value and the current value of B. And then similarly, since we're passing a mutable borrow for B here, we'd also like to say, well, the final value that's inside of B will be the same thing as the current value, the value at the moment that we're entering our function. So thus, B is unchanged. And with this, we can express fairly compact specifications for complex properties of immutable borrows or structures that return mutable borrows. And we'll see an example of that later. And then we can apply this in our verification in a rather natural way. So here we have a little sort of symbolic execution of our program with a little main function that actually shows our specification being applied for verification. So as we execute our code, we have on the right-hand side sort of logical hypotheses that we use in verification. We perform our two borrows before our function call for x and y. And as I said, the moment we create a borrow, we immediately reassign the final value of our borrow to the variable that we actively just borrowed from. And so here we created our two borrows, A and B, and we gave x and y the values v1 and v2, which are the final values of A and B respectively. And then we pass A and B to our function increment and recover the post condition as a result. That post condition informs us of the values of v1 and v2 after our execution, telling us, well, the final value of A must be 15, since it's going to be the value, the current value of A and the current value of B, and that the final value of B must have been unchanged compared to its current value. And using these new bits of information, we can easily conclude that X must be 15, that Y must be 5 as well. So that was a rapid overview of some of our specification language. Currently, we have support for basic or pre and post conditions, as well as loop invariants and variant annotations to help prove termination. We allow you to write, we can write specifications for code which involves immutable and mutable borrows, as well as box types. We don't support things like cell or ref cell. So we don't have any support for interior mutability. And we don't currently allow you to abstract over sort of unsafe types, that is types that use that use raw pointers somewhere inside and do interesting things with them. We also have support for logic functions. So those are going to be, I'll show an example of one of those in just a second. Those are functions which we write in Rust, but are interpreted as functions in our program logic. So as I said earlier, we don't currently allow you to perform abstraction of data types, which is particularly interesting for data types that involve unsafe sort of structures. And that's one of the things that we're currently looking at. So in particular, we're considering several different approaches on how to best fit those in with the rest of our work, and ensure that the verification work that has to be done by Rust programmers to show that these representations are preserved is not too consequential. And if anybody has sort of opinions on the best approach to attack this, I'd be happy to discuss this afterwards. But it's one of our active areas of work for the moment, as well as the related question of how we place invariants on our types and require certain properties of them. So all this is well and good, but can we actually prove properties on sort of more interesting programs? And so here is a little example taken actually from the Spark test suite. Well, their version is in Ada, of course, and ours is in Rust. But here, the idea is that we have a linked list composed of boxes to another element of our list. And we'd like to zero out every single cell in our list, and of course show that property formally, and that's the purpose of this small all zero function. But before we can actually write the specification for all zero, we're going to need a little bit of additional help to be able to better express it. And so this is where we use logic functions. And so our logic functions are going to be terms in our program logic in a function. They, as a result, must be pure and they must be total. And those will be verified by Creusot. You may also have noticed that the return type, for example, of our length function and the input parameter ix of get are of type int here. This is another addition in our program logic. It's int, the type of mathematical integers. So we have support for things like unbounded integers in our program logic. But as a result, you can see these two functions are rather simple. And so we define our length in a recursive manner, and get, which is just the nth accessor for our linked list, as well. So as I was saying earlier, our program logic is written in a subset of Rust. It's the subset that corresponds to the terms in our our logic functions are written in a subset of Rust corresponding to our program logic. Within those logic functions, we actually relax the ownership discipline of Rust. Since we're no longer in an executable context, we don't necessarily need to do things like enforce that certain types are copy or not. These aren't really corresponding to machine resources anymore, and we may actually want to refer to a certain value more than once in a specification. But we also have to impose a few additional guarantees, notably that our functions must be total, they must be pure. And to help you prove that your functions terminate, you can also you can use a variant annotation and help Y3 along with that, though often it's able to infer termination of your functions on its own. Very well. So back to our little all zero example. Now that we have our length helpers and our get helper to write our specifications, we can actually write the top level specification for all zero. And so here, what we'd like to say is that, well, all zero is, first of all, it's not going to remove or add any elements to our list. And so to that end, we say that the length of the final value of our list is going to be the same as the length of the current value of our list. That is to say, the mutable reference of our list hasn't actually added or hasn't caused any elements to be added or removed. And additionally, the key property that things are actually being zeroed out is the second ensures, which tells us that for every index inside of our list, when we look inside the final value of our list at that index, we're going to see 0. And so hopefully you're convinced that this property is the key property of all 0. And we have to make one final change in order to verify this, which is we need to actually annotate our loop with an invariant. And so we give it our two invariants, one for each of our post conditions. These invariants may look a little bit wordy, but all they're doing is encoding this little, they're encoding a magic wand from separation logic. And so it's a little trick, which basically is telling us that if we know that the property holds for the rest of the list, then we can sort of rebuild it for one additional step on our list. And in the end, it's just a little trick that we have to do when we're deconstructing our list in a loop. And using this, we can actually verify this in directly in Creusot. And so I'd like to show you this in person. So I'll just have to swap my screen share quickly. And show you everything I have. And so here we have the exact same code that I was showing you before, just in a single file, directly on our Rust code. And then we have that code loaded up in a Y3. Why is it not doing what I want? There we go. So we have this code translated to Y3. So as I was saying at the very beginning, the user experience is a little bit subpar for the moment in the sense that we still require you to operate on the actual translation to do your proving. But the nice thing is that your proofs tend to be very automatic. So here we have the translation of all 0 into our functional language. And on the left-hand side, we see the required verification conditions to prove our code. And we can launch an automated prover, which after about a tenth of a second tells us that everything's good. Our example is valid. So with this tool, we're able to verify sort of non-trivial programs involving pointers and data structures that involve pointers. We can handle things like loops over our pointers without any difficulty. Sorry, I need to see if I can share my just my slides again. Sorry about that. There we go. So as I was saying, we can verify semi-non-trivial programs involving pointers, but there's a lot of work that remains to be done. The project is still sort of just beginning. So our sort of current and ongoing, our current work and future directions are both. So as I was mentioning a little bit earlier, we're giving a new proof for the core translation of Creusot and that of Rusthorn in collaboration with one of Rusthorn's core core authors, Yusuke Matsushita, and the MPI SWS at Saarbrück. But we also have plenty of work to do in Creusot to support further features of Rust, in particular, things like traits and generics that have trait constraints, as well as hopefully interior mutability and other such more advanced and unsafe types. Yeah, thank you very much for listening to me. If you have any questions, I'd be happy to answer them.
Yeah, thanks, Xavier. There are a few questions, and we do have some time. Yeah. So Federico asked do you know if @fin annotations can be automatically generated from Prousty pledges, or the other way around?
So the other way around, I know that we can do it in the sense that we can write pledge as a simple logic function in our program logic. So we can definitely encode the after expiry pledges of Prousty. However, I've thought a little bit about this, but I haven't found a nice way of writing @now and @fin using pledges in Prousty. I'm not convinced that there's necessarily more expressivity. It just might be a more convenient syntax. And then to answer Ralph's question, which is he was asking if logic functions can mutate anything. Yeah, logic functions cannot mutate anything. They must be pure. They must be total. They can't have any sort of side effects, which includes mutation. One of the key ways we do this, we impose this restriction, is that we basically eliminate from our syntax any of the Rust expressions that could allow mutations. So there's no way to, for example, assign to a pointer or do any sort of assignment apart from let bindings in our logic functions. Yeah, and as Claire was saying, we can't create new cells either. All functions that are called within a logic function must themselves be pure. So it's a transitive property, which guarantees that, for example, box new would not be called from inside of a logical context. Yeah.
I could also re-ask the same question I asked on the Prousty talk, which is you specified again the list content in this all zero example via the get function, which seems rather indirect to me. Can I use like logic level lists or something like that?
So as I was saying, this is something that we're actively working on.
So that's one of the items there. Okay, I didn't recognize it, but I guess I don't know Y3 terminology. So
yeah, so it's one of the things that we're actively working on and we're discussing, and we have a few ideas on. There's a few choices on how we could go about adding this, and so we need to think a little bit about what would be most natural and what would impose the least verification work for users.
Cool. Do you know if you mentioned Spark is using this prophetic approach? That seems like the same approach at Rusthorn, basically.
Yeah.
Do you know if Spark, did Spark take that from Rusthorn or the other way around? Is this an independent reinvention?
No, Spark took it from Rusthorn through us, effectively.
Oh, okay. That's cool.
Yeah.
That's very nice.
Okay, any other questions? Okay, so let's we have a break coming up, which is going to be now 9 minutes from now. So we'll come back at 5 minutes past the hour.